Hi, good morning. Good morning. How are you? In the last couple lectures, we illustrated some applications of integration. We calculated the center of mass. We looked at how we could use integration in order to calculate work. We looked at surfaces of revolution and so forth. And in some examples, you notice that the integrals that we were getting were very difficult to calculate. In those examples, I suggested that you use Wolfram alpha so that Wolfram alpha can guess an antiderivative, and in some cases you could actually, or in principle in all cases, you can verify that the guess is correct by differentiation. So given any function, you can always differentiate it, and in Calculus 1 we developed a systematic way of doing so. Integration is more of an art rather than science, that sometimes you have to guess what could be an antiderivative. There are examples, actually many of them, that even Wolfram alpha cannot handle. Actually, mathematicians prove that there is a large class of integrals that cannot be computed using elementary functions. An example of such an integral is the integral of cosine t squared dt. In today's lecture, we will illustrate a technique called integration by substitution. That technique is a consequence of the chain rule, and it will allow us to handle some cases, such as, for example, t times cosine t squared. Let's look at our first example. Let's say that we would like to find the integral of cosine x squared times 2x dx. Can you guess what the general antiderivative of this function is? Well, remember, an antiderivative of cosine is sine of x, so maybe a guess would be something with sine, right? Let's try sine x squared. So if I were to differentiate sine x squared, how do I differentiate sine x squared? Sine x squared is a composite function, right? The outer function is sine, the inner function is x squared. So I need to apply the chain rule here, and the derivative of sine is, what is it? Cosine of x, right? So the derivative of sine x squared will be cosine x squared times the derivative of the inner function times 2x. And that's exactly the integrand that I have here. So because I know that the derivative of sine x squared is cosine x squared times 2x, then I can state that the general antiderivative of cosine x squared times 2x is equal to sine x squared plus c. Let's try one more example where we will guess an antiderivative. Let's look at the integral of the square root of x squared plus 1 times 2x dx. And I would like to give you a minute to try to guess an antiderivative of this function, and then we will try to guess it together. Has anybody guessed the general form of antiderivative of this expression? This one is a little bit harder, right? But let's see what's similar between these two examples. You have 2x, 2x, and here we notice that sine is an antiderivative of cosine, right? So if I can find an antiderivative of the square root function, maybe I will get a guess, and then I can check if that guess is correct or not. So what is the integral of the square root of x dx? What is it? It's x to the power 1/2, right? So it will be 1 over 1 plus 1/2 times x to the power 1 plus 1/2 plus constant c. So let me simplify this. This is 2/3 times x to the power 3/2 plus c. So then I wonder if maybe that integral will be equal to 2/3. Instead of x, I will put the argument here, x squared plus 1 to the power 3/2 plus c. Let's check if that guess is correct or not. So I need to differentiate 2/3 x squared plus 1 to the power 3/2 plus c. The derivative of c is 0, so I'm just differentiating this. And how do I do that? I have a constant here, 2/3, right? So I can factor it outside, and I just differentiate x squared plus 1 to the 3/2. So I will apply the chain rule. So the chain rule states that the derivative of just the expression x squared plus 1 to the power 3/2 is 3/2 times x squared plus 1 to the power 3/2 minus 1. So that is just 1/2. And then I need to multiply by the derivative of x squared plus 1. The derivative of x squared plus 1 is 2x. So if I simplify this, notice that I get the square root of x squared plus 1 times 2x. So in fact, I did get the integrand. Therefore, our guess is correct. Let's take a look at these two examples and see if we could write down a general pattern of these integrands, so that many other examples would fall into this category. And let's see if we could generalize our guess here. So clearly we have a product, right? We have a product of two expressions. The first part is a composite function. So in our example here, let f of x be cosine of x, and then g of x would be x squared. So how can I express this integral? That would be the integral of f of g of x times, again, 2x is what? That's the derivative of g. So I have the integral of this form, a composite function, the composition of f and g, and the derivative of the inner function g. I'd like to give you a second to determine what f and g are for our second example here. Anybody? What's f of x? The square root of x. Let's see. So if I let f of x to be the square root of x, and then if I let g of x to be x squared. Well, let's try that. Then what would be the square root of x squared plus 1? So this integral would be then the integral of f of g of x plus 1, then times g prime of x. Well, this is not exactly the same pattern as the upper example here. So maybe g of x should not be equal to x squared. X squared plus 1. Okay, let's try that. Then the first term will be f of g of x. So there's no plus 1 anymore. And the second factor is still 2x, which is g prime of x. So notice that both examples follow the same pattern. And it is this pattern that we will look for in today's lecture. Whenever we will have this pattern, I will show you that the chain rule will imply that we can calculate this integral by finding an antiderivative of lowercase f. So if I denote an antiderivative of f by, say, f, capital F, so in other words, capital F is equal to lowercase f, then I will show you that this integral is simply equal to capital F of g of x plus c. So in other words, capital F here in our first example was sine, right? Because the derivative of sine was cosine, was lowercase f. And in our second example, capital F was, what was it? It was 3/2 times x squared plus 1. No, sorry. It was 2/3 times x squared plus 1. No, what was it? Lowercase f is equal to the square root of x, right? So what's an antiderivative of that? I think we did this calculation right here. So uppercase f is 2/3 x to the power 3/2 plus c. So notice that this expression is, this expression is simply equal to capital F of g of x plus c. And in our first example, sine x squared is equal to capital F of g of x plus c. So the pattern that we have here is to identify f and g in the integrand, and then find an antiderivative of f, and then the answer will be capital F, which is the antiderivative of lowercase f of g of x plus c. Let me state formally the generalization of these two examples as a substitution rule. And then I will illustrate how we could apply the substitution rule in practice by introducing a different variable. Let me state the substitution rule that we will use in today's lecture. So I will introduce a new variable. I will call the inner function g of x, I will call it u. And let's say that this function g is a differentiable function on some range which is an interval. Let me call that interval I. And let's assume that the outer function f is continuous on that interval I. Then, whenever we have the integral of the form that we discussed earlier, so f of g of x times g prime of x dx, then we could calculate this integral by calculating the general antiderivative of the function lowercase f. So this would be equal to the integral of f of u du. So the right-hand side is an antiderivative of lowercase f evaluated at g of x. Let me illustrate why this formula holds true in general, although we got a sense why that was the case by looking at the first two examples. It's basically the chain rule. So how does one argue this? Well, let capital F be an antiderivative of lowercase f. So what does this mean? This means that f, capital F prime, is equal to lowercase f. And remember the chain rule. The chain rule states that if you have the function f, capital F, of g of x, when you differentiate the composition like this, I will use the Leibniz notation for the derivative. And what do? You take the derivative of the outer function, evaluate it at the inner function, and multiply it by the derivative of the inner function. So I'm going to write the chain rule backwards, right? So I get f prime of g of x times g prime of x. So this is the chain rule. But f prime is lowercase f, so then I get f of g of x times g prime of x, right? This is equal to the derivative of capital F of g of x. But what are we looking for? In our statement, we want to compute the integral of an expression that looks like this, right? So we want to calculate the integral of the left-hand side. So why don't we integrate both sides? If two functions are equal to each other, then their integrals must differ by constant, right? So from this equation, we get that the integral of f of g of x times g prime of x dx is equal to, what's the integral of the right-hand side? Well, the general integral, the antiderivative, is the opposite operation to differentiation, right? So if I take an antiderivative of the derivative, what do I get? I get the function that I'm differentiating, but since I'm talking about a general antiderivative, I need to add a constant. So the right-hand side then is equal to capital F of g of x plus some constant c. But the right-hand side, capital F being an antiderivative of lowercase f, the right-hand side is actually exactly equal to the integral of lowercase f. But once you get that antiderivative, we're evaluating it at g of x, which is u. So let me write this down. So this is just the integral of f of u du. And that's because the derivative of capital F is equal to lowercase f. So notice that I got the left-hand side is equal to the right-hand side here. And that's precisely the statement of the substitution rule. In a couple of weeks, when you perhaps may forget the derivation of the substitution rule, just remember that the substitution rule is a consequence of the chain rule. We will now move to a series of examples. We are going to apply our substitution equation to redo example number 1 from the introductory part of the lecture. The key idea and the main difficulty in the substitution method is to pick the right substitution. In other words, you would like to introduce a new variable, variable u, so that the resulting integral will be easier to calculate. You look for a composite function as part of the integrand, and then you try to see what's the inner function. And that inner function typically will be given by our new variable u. Okay, so let's see. Here the composite function is cosine of x squared. So the outer function is f, which is cosine, right? And the inner function is g of x, which is equal to x squared. And I'm letting my new variable u to be x squared. So then the derivative of x squared is 2x, right? So I need this g prime here. In Leibniz notation, du by dx is equal to 2x. Okay, so according to our substitution equation, the left-hand side, let's see if the left-hand side matches. If cosine of u is f of u, so here cosine x squared is f of g of x, which is u, times 2x, which is the derivative of g of x. So notice that this expression and this expression are identical. It's just that I wrote the derivative of g in Leibniz notation. Let me rewrite our substitution equation in Leibniz notation. So the integral of f of u du by dx is equal to the integral of f of u du. So this, by our substitution rule, is equal to, what's the right-hand side? The integral of f of u du. Okay, so f is cosine of u du. So what's the integral of cosine? Sine, right? So this is sine of u plus c. And of course, since we started with a function of x, we need to end up with the function of x. So in the substitution method, do not forget to return back to the original variable. So let me replace u with what u was. U was x squared, right? So what I get is sine of x squared plus c as my final answer. So notice that the way I wrote down this example, I don't have to even specify this function g of x. The g of x is just given by the right-hand side in the substitution. This is a substitution method because I'm replacing a more complex integral with a simpler integral by using a new variable. And in this case, new variable was x squared. Notice that it's very easy to remember the substitution method by looking at this equation in Leibniz notation. So the integral of f of u times the derivative of the function g of x, which is u, so du by dx. So that integral is equal to the integral of f of u du. And if I could, for a moment, just cancel dx here and dx here, then certainly the left-hand side would be equal to the right-hand side. So that's why it's easy to remember the substitution rule. Do you have any questions? Okay, so let's look at another example. This time I integrate 3x squared times cosine of x cubed dx. I'd like to give you a second to determine the right substitution and the outer function of the composite part of the integrand. So can we think of this product as the product of a composite function times the derivative of the inner function? Well, here we have a composition, right? So maybe I should just rewrite this as the integral of cosine x cubed times 3x squared dx. And then it's clear that the composite function is f of x to the third power, so cosine is f, and then u would be x cubed, and let's see if that substitution will work. So our first guess would be that I need to let u to be x cubed. Then notice that for the substitution method I need the derivative, right? So du by dx is equal to 3x squared. So this part is du by dx. And the whole thing, cosine of x to the third, is f of u, right? Okay, and the substitution rule tells us that this integral can be replaced with a simpler integral, which is the integral of f of u. So cosine of u du. And again, the integral of cosine u du, as I wrote down earlier, is equal to sine of u plus c. So don't forget to return to the original variable. So the answer is sine of x cubed plus c. In our third example, we will find the general antiderivative of 2x times root of x squared plus 1. Again, a key idea here is to find the right substitution. We see the integrand as a product, but the second factor is more complicated, so probably that would be a composite function, and 2x probably be the derivative of the inner function. So in order to rewrite our integral in the form stated in the substitution rule, let me change the order of the factors here. So it's the integral of x squared plus 1 times 2x dx. So the outer function of the first factor is the root function, right? So f of u is equal to the square root of u, and the substitution that might work, we'll check if it works, we replace x squared plus 1 with u. So then the derivative of x squared plus 1 is 2x, right? Because the derivative of 1 is 0. So this is f of u. This is du by dx. So by the substitution rule, we get a simpler integral, which is the integral of f of u du. F of u is the square root of u. So we get just the integral of the square root of u du, which is, it's like u to the power 1/2. So we get 1 over 1 plus 1/2 u to the power 1 plus 1/2 plus c. Remember how I got this formula? In general, the integral of u to the power n du is equal to 1 over n plus 1 u to the power n plus 1 plus c. Here n is equal to 1/2, right? Okay, so we get 2/3 u to the power 3/2 plus c. We're almost done, but don't forget to replace u with the original, with the function of the original variable, right? So it'd be 2/3 x squared plus 1 to the power 3/2 plus c. It's a good idea to check your answer by differentiation. Do you have any questions? Notice that I could interpret this equation and group it as following. 2x dx, I could think of it as just du. And the square root of x squared plus 1, that's f of u. Any questions? So let's move to another example. Let's look at our next example. This time we will calculate, using our substitution rule, the integral of the square root of 3x plus 1. So here we just see a composite function. We don't see the derivative of the inner function. But let's try to find a substitution anyway, and let's see what happens. And it makes sense to let u be equal to 3x plus 1. So then f of u will be what? The square root of u. So let's see if we have the integral of the form ready for the substitution. So what do I need to do? I need to calculate the derivative of 3x plus 1. The derivative of 3x plus 1 is 3. So I don't have that integral. But on the other hand, if I was asked to integrate this, the square root of 3x plus 1 times 3, dx. Then 3 is the derivative of 3x plus 1. So this integral matches the form that we need. So what do? Why don't I just write this integral as this one and multiply it by 1/3? So this is equal to 1/3 times the integral of 3x plus 1 times 3 dx. So this is then equal to I'm replacing 3x plus 1 with u. So it'd be 1/3 the integral of the square root of u times 3 is the derivative du by dx. So the substitution rule tells me that this is just the integral of the square root of u du. So I got 1/3. What was the integral of the square root of u? 2/3 u to the power 3/2 plus c. So our final answer is 2/9 u to the power 3/2 plus c. Is that our final answer? No, because we have to return to our original variable. So we get 2/9 3x plus 1 to the power 3/2 plus c. And you can check that, in fact, if you differentiate this function, that you get the square root of 3x plus 1. Any questions? Notice that the substitution rule here, if you compare the left-hand side and the right-hand side, the substitution rule states that formally you can replace the derivative of g dx with just du. In other words, if I were to write this equation du by dx as du is equal to 3dx, although technically for us it doesn't make sense, but the substitution rule says that, okay, well, if for a moment you formally allow me to write du is equal to 3x, and then I will replace 3dx with du, that's okay. That's okay because of the substitution rule. So typically, a lot of textbooks simply, when they say use the substitution u is equal to 3x plus 1, rather than writing du by dx, the derivative, they just write du is equal to the derivative of the function g dx. So again, the reason why this makes sense is because of the substitution rule. Let me illustrate one more example where I will treat du and dx as if they were variables. In our next example, we integrate e to the power 2015 times x dx. And this time I will treat du and dx as if they were separate variables. And again, I can do that because of the statement of the substitution rule. So I see a composition here. It's the exponential function, that would be the outer function, and the inner function is 2015x. So probably it makes sense to let u to be equal to 2015x. So then if I differentiate, du by dx is equal to 2015. But again, I said that I will permit myself to write du and dx separately. So du is equal to 2015 dx. So then our integral will be the integral of e to the power u. And now I need to replace dx with du times something, right? So from this equation I can find what dx is. Dx is equal to 1 over 2015 du. So then I get e to the u times 1 over 2015 du. Okay, 1 over 2015 is a constant, so I can take this outside of the integration, and then I get 1 over 2015, the integral of e to the u du. So that is a simpler integral, and you know that the integral of e to the u du is just e to the u. So my final answer is 1 over 2015 e to the u plus a constant, right? But I need to replace u with what u was. So u was 2015 x. Maybe let me write down the intermediate step before I write the final answer. So the intermediate step was that the integral of e to the u du is equal to e to the u plus c. So this is equal to 1 over 2015 times e to the 2015x plus c, but this c is not the same as this one. Do you have any questions? There will be many examples where your first guess of a substitution will be wrong. It's okay to guess wrong. There is no consistent method here of finding the right substitution. It's a little bit like an art here. In the last part of the lecture, let's calculate a few definite integrals using the substitution method. Notice that now as we can find antiderivatives, we can then find the definite integrals as well using the fundamental theorem of calculus. Let's start by looking at the definite integral of e to the power 2015x again, but well, we'll have limits of integration, right? Say from 0 to 1 of e to the power 2015x dx. Remember, the fundamental difference between the two integrals is that this represents a collection of functions, whereas this integral is a number. And that number is actually the area under the graph of e to the power 2015x between 0 and 1. So one way to approach this problem is if say g of x is an antiderivative of e to the power 15x. So in other words, if g prime of x is equal to e to the power 2015x, then what I need to do is I need to subtract g of 1 minus g of 0, right? That is the fundamental theorem of calculus. But I know what g is, right? I can pick g to be this, because I already calculate the general antiderivative of our indefinite integral, e to the power 2015x. So then I get g of 1 will be equal to what? If g of x is equal to e to the power 2015x divided by 2015, so g of 1 is equal to e to the power 2015 divided by 2015. And then g of 0 is e to the 0 over 2015, which is, no, it's not 0. E to the 0 is 1. So I get this expression, and perhaps you could, if you want, you can rewrite this as e to the power 2015 minus 1 divided by 2015. There's another way to evaluate definite integrals using a substitution method. And that second method is usually more convenient than what I just illustrated here. So let me state a general theorem, and then I'll illustrate a couple more examples. Let's consider the definite integral f of g of x times the derivative of g dx. And the limits of that integration go from a to b. And I'd like to have a substitution statement for this definite integral. So in order for the substitution statement to work, I just wrote down the assumptions that are necessary, but in case of our homework problems, most of the time these assumptions will be satisfied. So we're assuming that the inner function has a continuous derivative on the interval on which we integrate, and we're also assuming that f is continuous on the range of g. So if we let our new variable u to be equal to g of x, then this integral will be equal to the integral of f of u du. Well, so far the same expression on the right-hand side as in the previous theorem when we talked about substitution for indefinite integrals. But the left-hand side is a number, right? So the right-hand side must be a number. So the limits of integration here has to be set. And what's important is that you evaluate this integral not at a and not at b, but at g of a and at g of b. Let me illustrate one more example. Let me illustrate an example of how we will use the substitution rule for definite integrals, and I will pick the following. The integral from 0 to pi divided by 2 of 3 sine 3x dx. What do you think? What should be our first guess for a substitution. Well, notice that sine 3x is a composite function here, so it makes sense that the inner function be 3x. So we let u to be equal to 3x. And then the derivative of the inner function is 3. So basically this integral is almost ready for the substitution formula, except that I should probably write sine of 3x first. So let me do this. So then according to our substitution rule, the integral will be simplified by just writing the integral of the outer function. And the outer function here is f is equal to sine. So that would be the integral of sine of u du. And many students here will make a mistake. They will just write 0 to pi divided by 2. And that's wrong. It's wrong because you need to evaluate the new integral not at a and at b, but at g of a and then g of b. And here the inner function g of x is equal to 3x. So I need to evaluate at 3 times 0 and then at 3 times pi divided by 2. In order not to make this mistake, I would suggest to write the limits of integration as x is equal to 0 to x is equal to pi divided by 2. And then here, you will remember that now I need to write the limits for integration for the variable u. So u is equal to, and you find out what u is equal to because it's g of 0, right? See, here the lower limit is g of a. And the upper one is u is equal to g of the upper limit, so g of pi divided by 2. So g of x here is equal to 3x. So if I don't want to write what g is, I need to evaluate what is u when x is 0, right? So u is equal to 3 times 0 to 3 times pi divided by 2. So now we get the integral of sine of u. Well, we had that integral several times already. No, we actually had the integral of cosine of u. So what's the integral of sine of u? It's negative cosine, yes. Negative cosine of u. And now we evaluate that antiderivative at u is equal to 0 and at u is equal to 3 pi divided by 2. And then we take the difference. So we get negative cosine of 3 pi divided by 2 minus negative cosine of 0. What's cosine of 3 pi divided by 2? Well, let's try to remember the trigonometric circle. So here is a point corresponding to 3 pi divided by 2. So this is pi, and it's pi and a half. So that's this point, right? So that's the angle 3 pi divided by 2. And if that point has coordinates, what are the coordinates for this point? Cosine of the angle and sine of the angle, right? So in this case, the coordinates are 0, -1, and which one is cosine? It's the horizontal coordinate. So cosine of 3 pi divided by 2 is 0. And cosine of 0 is 1. So the answer is 1. Let me try one more example. The integral from 1 to e of natural logarithm of x divided by x dx. And actually, when I look at this example, it's not evident that this would be a good example for the substitution method. Because I don't see a composite function. But one thing that comes to my mind is that if I differentiate ln of x, I get 1 over x. So if I were to rewrite this as ln of x times 1 over x dx, then perhaps, since that's the derivative of ln of x, if I let u to be equal to ln of x, then 1 over x dx, 1 over x is the derivative of du by dx, so this by substitution method will be just du. But where's the outer function of the composite function? Here I have ln of x, but I don't have anything else. Is that a problem? Well, we can always write ln of x as the composition of ln of x with the identity function. So if you would like to match this expression with our substitution formula, we just let lowercase f to be the identity function. So I can write this down, that f of u is just equal to u. And then g of x is equal to ln of x. Okay, so let's apply our formula here. Remember to keep track of the limits of integration. So now I'm replacing everything with, and I'm writing everything in terms of u. So I need to write the limits of integration in terms of u. What was our substitution? U is equal to ln of x. So if x changes between 1 and e, then u will change between, if x is 1, then u is equal to ln of 1. What's ln of 1? It's 0. And ln of e? The natural logarithm of e. E to what power gives you e? 1, right? So then I just write f of u du. So f is what? F is just u. So it's just u du. And this, you know what it is, right? The integral of u is 1/2 u squared, and then you evaluate this between u is equal to 0 and u is equal to 1. So it is 1/2 1 squared minus 1/2 0 squared and that is just 1/2. There's no better method to learn the substitution rule other than practicing lots of examples. I only gave you a few problems in the homework, but please go over many other homework problems and watch other videos on YouTube if you get stuck as well.